Myself Rakhi, Assistant Professor in the Department of Electronics and Communication Engineering, ABS Engineering College, Ghaziabad, affiliated to Dr. APJ Abdul Kalam Technical University, Lucknow. Today in the lecture series of Optical Communication, we are going to discuss about Kerr effect and the introduction part of the dispersion. The topic which I am going to cover in this particular lecture is the Kerr effect, types of Kerr effect and introduction to dispersion. So, before proceeding further, just have a recap of the attenuation section which we have discussed in the earlier classes. In the earlier classes, we have gone through the different type of attenuation which comprises the signal losses at the from the input end to the output end. So, we have gone through the many types of the attenuation form, bending, and we have gone through the absorption mechanism, we have gone through the scattering, and in this particular we are going to discuss about one of the effect which is known as the Kerr effect, and it is named after the scientist who first discovered it and formulated it accordingly. So, Kerr effect. Kerr effect comes under the category of non-linear effect. Already we have discussed about the non-linear types of scattering. Non-linear scattering, as we discussed in the last lecture, is that type of scattering in which input and output system are connected with each other non-linearly, and it is follow the non-linear principle. And in this effect also, it is the non-linear effect, that means input and output are related to each other non-linearly. And non-linear system is that system in which output is not proportional to the input. So, in this particular system also this is happen ki output is not dependent upon the input, is not proportional to the input. So, it is a non-linear effect which can be described by the intensity dependent refractive index. So, this is the main point here, intensity dependent refractive index. Already we have a knowledge about the refractive index. Refractive index of the medium decides its propagation form. Already we have a knowledge that refractive index of a core should be greater than the refractive index of the cladding for the proper TIR, which is the main principle behind the optical communication. So, if the refractive index of the fiber changes as per the intensity, these are referred as the Kerr non-linearities. So, again non-linear effects, that means Kerr effect is a non-linear effect which can be described by the intensity dependent refractive index of the fiber. Kerr actually gave the condition that refractive index of the fiber, which comprises the refractive index of the core and the cladding, changes as per the intensity. That means it will be have a refractive index will have a different value at the lower intensity of light and at the higher intensity of the light. Refractive index of the medium results from the applied optical field perturbing the atoms of the molecules of the medium to induce an oscillating polarization. The polarization basically means providing direction to the light rays. If we are saying that certain light rays is polarized, that means we have already provided some particular direction so that it can move in that particular direction only, and it will not distracted direction, which then radiate producing an overall perturbed field. So, refractive index of medium results from the applied optical field which induces an oscillating polarization, means with the polarization is actually straightforward path, that means we are providing a particular path to the light ray. But if that light ray started oscillating due to applied optical field, a new field is get created. At low intensity, so we have discussed in the first line it was written that as per the intensity of light, refractive index of the fiber changes. So, at low intensity the polarization is linear function of the applied field. So, the polarization is now oscillating. At low intensity, polarization is a linear function of the applied field. Polarization is changing as per the field applied to it, optical field applied to it. So, at the low intensity, polarization is a linear function of the applied field and hence the resulting field can be realistically described by a constant refractive index. At low intensity, when the polarization is a linear function of the applied field, in that case the resulting field can be described by a constant refractive index. That means there will be no change in the refractive index, but at the higher optical intensity, perturbation do not remain linear function of the applied field and the Kerr non-linearity effect can be observed. So, at higher field, at higher optical intensity, the perturbation of the field does not remain a linear function of the applied field and in that case Kerr non-linearity can be observed. So, we can easily say at this particular instant that if we want to reduce the Kerr effect in any sort of optical fiber propagation, then we have to maintain the intensity of optical light low. We have not to increase the intensity of optical light because it is most promising, it is most prominent in the case of a higher intensity of optical. At the low intensity, its value is relatively negligible or we can say low. Now, there are three different types of Kerr effect. First one is the self phase modulation, second one is the cross phase modulation, third one is the four wave mixing. So, before going through, just have a recap of the modulation. Modulation means some changes. In general terms, we can say that if there exist some changes, then only modulation can be used. So, modulation occurs in the field of communication in the form of amplitude, phase, frequency, etc. In that case, basically there exist some changes in the case of amplitude and phase and frequency. When we are talking about the phase modulation, that means there will be some, if we are taking that initial phase is the phi, then at the output we will have phi, along with that also we have a phi minus phi 1, phi plus phi 2, or we can say phi plus phi 1, phi minus phi 2. So, there will be a change in the phase when we talk about the phase modulation. So, we can in general terms we can see that when there is a change, then it is called as the modulation. Self phase modulation and the cross phase modulation. Phase, that means there should be some changes in the phase of the light ray propagating, and self means within, which is initiated from within, and cross means with someone else. So, these are the, and here is the mixing terms, that means of course there will be a mixing of the light ray. So, this is a general terms and we can interpret is exact what they want to say with the general terms also. So, just have a look at the next one, the first one, that is the self phase modulation. So, what the self phase modulation says? The intensity dependent refractive, of course it comes under the Kerr effect category. So, it will be a intensity dependent refractive index, causes the intensity dependent phase shift. So, we have a intensity dependent refractive index, it causes the intensity dependent phase shift in the fiber. So, as a name, phase modulation. So, of course, there existing a phase shift. Hence, for a light pulse propagating in the fiber, Kerr non-linearities result in different transmission phase of the peak of the pulse compared with the leading and the trailing pulse edge. Means this is the leading pulse edge and this is the trailing. This one is called as the leading or in the form of a pulse, leading, trailing. This one is the leading one and this one is the trailing one. So, what they say that the light pulse propagating in the fiber due to Kerr non-linearity will have a different phase. जो light pulse propagating inside the fiber will have a different phase than the leading and the trailing pulse edges. That is why it is a change in the phase of the pulse propagating inside a fiber. That is why it is called as a phase modulation. So, again why it is called as self? We have understood that why it is called as phase modulation. Then it remain what is called as self phase modulation. This effect is known as self phase modulation because it occurs does not have interact with other pulse. Whatever changes is occurring within the single pulse itself and it does not interacting with the other pulse here. That is why it is called as the self pulse. SPM, that is self phase modulation, what it can do? It can broaden the frequency spectrum of the pulse. So, what will be the result of the SPM? That is self phase modulation, which is one type of the Kerr effect, that is it broadens the frequency spectrum of the pulse. So, whatever broadening is the most important term. The spectral broadening caused by the SPM produces dispersion like effect, because dispersion, what the dispersion actually do, which we are going to discuss in the coming slides. In the dispersion itself, whatever be the signal at the input end, in the dispersion itself, what is going to be happen? If it has a this type of pulse at the input end and it goes inside a transmission medium of, then after passing through the transmission medium and after going through the dispersion mechanism, what is going to be happen? Its pulse width is increased now as per the initial one. We can easily see this in this diagram and this is called the pulse broadening. So, only this type of effect can be seen with the self phase modulation also, which can limit transmission rates. What are the limitations then occur? It limits the transmission rate in a long haul optical communication, because and dispersion also, this is applicable to dispersion also. Dispersion can be most importantly can be seen in a long haul optical transmission. For short distance transmission, dispersion is also less, and when we take a long distance transmission, dispersion also increases as per that, and this is applicable to self phase modulation also. Depending upon the fiber type also and its chromatic dispersion, this is a type of a dispersion. Chromatic dispersion is a type of dispersion which we are going to discuss in the coming lectures or slides. Now comes the cross phase modulation. So, basic things which are applicable with the modulation is applicable here also for XPM, cross phase modulation, and again phase. So, what first of all we have to read it just like what the difference between a self phase modulation and a cross phase modulation, because in both the cases modulation is occurring in the case of in terms of phase only. So, what is happening here? Cross phase modulation is a similar effect as per the SPM, of course, because both of them are the phase modulation, except that the overlapping but distinguishable pulses possessing, for example, different wavelength or polarization are involved. Here what is happening? A single pulse is involved, single, which can be distinguishable, but in this case what is happening? there is overlapping may occur of different wavelengths and polarizations are involved. Light rays of different wavelength and polarization are involved, and in the cell phase same polarization and same wavelengths are involved. So, this is the basic difference between a SPM and a XPM. In this case, variation in the intensity of one pulse will modulate the refractive index. This is applicable to all type of Kerr effect, that is intensity variation will affect the refractive index of the fiber, which causes phase modulation of the overlapping pulse. It is called the phase modulation of the overlapping pulse. As the SPM, this phase modulation translates into frequency modulation, which broadens the pulse spectrum. Same as the SPM, in this case also phase modulation translates into the frequencies modulation and broadens the pulse spectrum. That means, whatever with the signal at the pulse width at the input, it gets broadens in this case also. XPM is exhibited as a crosstalk mechanism between the channels. Why it is called as a crosstalk mechanism? Because here there exists a overlapping of different wavelengths of lights. That is why, and whenever two different wavelengths or different frequencies of signals are overlap each other, then their information is not able to distinguishable. Then in that case we can't able to distinguish between two different signals, and this condition is called as the crosstalk mechanism between channels. When either intensity modulation is used in the, of course, dispersive optical fiber transmission, dispersion is involved. Dispersion also overlapping takes place, and we can't able to distinguish between the two adjacent signal. Strength of XPM increases with the number of channel, and it also becomes stronger as the channel spacing is made smaller. So, if we want to look at this particular statement, see the last statement, strength of the XPM increases with the number of channels involved. Number of channels involved means number of light rays of different wavelengths increases. Light rays of different wavelength increases now. Wavelength. Then only number of channels increases. And if number of wavelengths increases, and this is a different wavelengths and polarization are involved with the. So, if we keeps on increasing the number of light rays of different wavelength, then of course, this cross phase modulation increases and becomes stronger as the channel spacing is made smaller. If what I am going to say, if we take this digital modulation case, digital signal, in this particular case, the channel spacing between the pulse is wide. So, in that particular case, after XPM, it for long haul this communication only, we can see that this pulse and this pulse get overlapped. It takes time because this distance is more, but if we reduce the distance, if we reduce this spacing between the two pulses, then overlapping takes less time. That is why it is saying that XPM increases with the number of channels and becomes stronger as the channel spacing is made smaller. So, what we have learned in this particular part, that if we have to reduce the XPM type of Kerr nonlinear effect in the proper optical communication, then we have to reduce the number of channels, because that means number of wavelengths of light rays that is entering into the fiber, that should be less, and channel spacing should also be less. Now, comes the 4-wave mixing. So, what is meant by the 4-wave mixing? We are going to have this beating between light at different frequency of wavelength in multi-channel fiber transmission causes phase modulation of the channel, and hence the generation of modulation sideband at new frequency, which are termed as a 4-wave mixing. So, as we have discussed in the first two cases of the Kerr nonlinearities, that is in the case of a self phase modulation and the cross phase modulation, what is going to happen? That phase translates it into the frequency and the pulse broadens. So, phase translates itself into the frequency and the pulse broadens. So, in this case what is happening? Whenever the phase modulation or the frequency modulation, just look at the frequency term here. Frequency initial is 1 f. If the modulation takes place, if it has a initial frequency of f, and if the modulation takes place, what is going to happen? F minus f1, f plus f1. So, f minus f1 are the adjacent frequency to the f's. For first one is the f minus f1 will be in the smaller value and f plus f1 will be the higher value. Similarly, f minus 2 f1 or f plus 2 f1. So, these are the conditions which occurs when we have a frequency modulation, and this will occur as a sideband because f initial one, and if we take any frequency which is adjacent to it, it will be represented as a sideband to it. So, generation of modulation sideband at new frequency, of course, it will have a new frequency which are termed as the 4-wave mixing. This frequency combination can be problematic for multi-channel optical communication as they become phase matched if the channel wavelength are close to the 0 dispersion wavelength. So, what is the problematic condition which arises in the multi-channel? This is not for the, this condition will not be problematic for the single channel optical communication. It will be problematic for the multi-channel because in the multi-channel it is may possible that this frequency may exist and it get matched, phase matched with the it. It is possible in the multi-channel only. Although FWM, that is our 4-wave mixing is a weak effect. It can accumulate when multi-channel signal remain in phase with each other over long distance transmission. So, we can easily say that each type of dispersion, this non-linearities, current non-linearity can be reduced by reducing the distance between the input and the output terminals. Now, the most important type of attenuation, that is the dispersion. And what is this? Dispersion of a transmitted optical signal causes dispersion of both digital and analog transmission along optical fiber. That means, it is applicable for both analog and digital communication signal. Optical fiber transmission which involves some form of digital modulation, then dispersion mechanism within the fiber causes broadening. That means, whenever dispersion is involved, so dispersion causes the broadening of the signal as they travel along the channel, and if we goes on increasing the distance between the transmitter end and the receiver end, the broadening goes on increasing as per that. Each pulse broadens and overlap with its neighbors, eventually becoming indistinguishable at the receiver input. What is happening? Each pulse broadens and get overlapped with the adjacent pulse, and at the input terminal of the receiver end, it become difficult for us to distinguish between the two pulses because they get overlap with each other so much. This effect is known as inter-symbol interference or ISI. So, this condition is known as a ISI, and this is a very important term, and you have to always remember this, what is meant by the ISI. Then in that case, you have to write, during the dispersion process each pulse broadens and overlap with the neighbors, so that at the receiver end input it become very difficult to distinguish between the two adjacent signals, and this is known as the inter-symbol interference or ISI. There are basically two type of dispersion. First one is the intramodal and the second one is the intermodal. Intramodal dispersion is also called as the chromatic dispersion. Now, here is an example of dispersion or ISI. This is the amplitude. What is here? 1 0 1 1. So, we can easily say signal is 1 here, then it is 0 in this particular case, 1 and 1 here. We have plotted the graph with respect to amplitude versus time, and what is going to happen now? If it start moving, what is at the next instant of time, what is going to happen? There the distance between these two pulses is reduced now, and distance between these two pulses also get reduced. So, what is going to happen now? These two pulses get overlapped towards each other, and if we goes on increasing, then again this distance is also get minimized and overlapping keeps on increasing. And for no overlapping condition, what should we have to done? We have to keep optical fiber link digital bit rate, that should be less than the 1 by reciprocal of the pulse duration. For the bit rate should be less than the reciprocal of pulse duration, and similarly it can be written as this way also, where sigma is our RMS pulse width. Now, this is the example of dispersion in each type of fiber. This is the multimode step index fiber, this one is the multimode graded index fiber. These are the different types of fibers, and this is the single mode fiber. We can easily see this is the input and this is the output one, output, input and output. We can see that the dispersion is most in this case, that is multimode step index fiber, and it is least in this case, in the case of a single mode step index fiber. So, these are the about which how it is happening, we will discuss in the coming lectures. Now, let us do a numerical related to that. In the multimode graded index fiber, which exhibit total pulse broadening of 0.1 microsecond over a distance of 15 kilometer, estimate you have to calculate the maximum possible bandwidth of the link, that is you have to calculate BT, pulse duration per pulse dispersion per unit length, and bandwidth length product of the fiber. So, for calculating the maximum possible optical bandwidth, just have a look at the formula which we have. BT should be less than the reciprocal of pulse duration. We have taken this one, tau is shown here 0.1 microsecond, substituted that one here, we will get the maximum possible optical bandwidth as 5 megahertz. And in the second question it is called pulse duration per unit length. This pulse duration is for 15 kilometer, and if we want to calculate it for per kilometer, then pulse duration 0.1 microsecond is divided by the total length, total distance, and we will get this. And the third question, bandwidth length product for the fiber. Already we have calculated the bandwidth is 5 megahertz and length is 15 kilometer. By taking the product of that, we can have a bandwidth length product. So, this is a very simple numerical which is dependent upon the values only and the formulas. Thank you for attending today's class. In the next class, we will go through the different types of dispersion.